deriving velocity and position from acceleration. All of these plots are simulated in LabVIEW. Real experimental data will be shown later. This is a cosine function with amplitude equal to 1 and frequency of 10 Hertz. This function, acceleration 2, will serve as the simulated acceleration signal. Velocity 2 is the integral of acceleration 2. Integral of cosine function is a sine function. Position 2 is the integral of velocity 2. Integral of sine function is a negative cosine function, but the ramp is not expected. This ramp is caused by an imperceptible constant, DC bias, in velocity 2. Integral of a constant is a ramp. So, our measured position from accelerometer data is contaminated by this undesirable ramp. Before we consider a solution, note that the derivative of position 2 is velocity 3, which is the same as velocity 2. Not surprising that the derivative operation is the inverse of the integral operation. Also note that the derivative of velocity 3 is acceleration 3, which is the same as acceleration 2. Not surprising again that two integrations followed by two derivatives yielded the same function. Back to our ramp problem. If we determine the ramp and then subtract it, the desired sinusoid without the ramp can be calculated. The least squares linear fit is this function, and subtract it from position 2 yields the measured position without the ramp. And taking two derivatives yields the original velocity and the original acceleration. All of these came from the simulated cosine function. If the simulated cosine function is multiplied by an exponential, then a more realistic scenario can be investigated. This is the original cosine function multiplied by the exponential function yields a damped sinusoid. This damped sinusoidal acceleration is a common response like a cantilever beam recovering from a shock. An accelerometer could measure this acceleration. And now we can integrate 2 times to get velocity and position. The DC bias is apparent in this more realistic signal, which results in the undesirable ramp in the measured position. But it can be subtracted out in the same way as before. As a final check, take 2 derivatives, which return the original velocity and acceleration. Here's the LabVIEW program that did all this. Understanding it will be easy. The cosine function with 1,000 data values in 1 second is generated here. A dynamic array containing 1,000 data values and time of 1 second is transmitted by the blue wires. The cosine function is plotted. Dynamic data is converted into an array of double precision numbers. Sample time is extracted. The first integration is performed. That yields velocity. The second integration is performed. That yields position. The first derivative is performed. That yields velocity. The second derivative is performed. That yields acceleration. The least squares best fit of position 2 is determined here and then subtracted here. A derivative produces velocity 4, another derivative produces acceleration 4. The bottom half of the program is the same as the top. After creating the exponential function and multiplying it by the original cosine function. A LabVIEW program has been used to demonstrate how velocity and position can be extracted from acceleration data. A simple solution of ramp removal from the integrated data was also demonstrated.